Over break, get your hands on the second book, The Theory of Almost Everything by Robert Order, because we're going to start readings in that right after break. If you actually get that book and read chapters 1, 2, and 3, which are actually short introductory chapters, it'll be a really nice review for the midterm, because it just covers the introduction to quantum mechanics. We're going to jump in after break, probably around chapter 4. But the first 3 chapters are good for that. The exam is Monday after break. Anybody who wasn't here last time who needs the sample questions for the midterm? All right, I will post those to the Blackboard site for the class in case you lose those. I will also post the quantum weirdness paper to Blackboard in case you need to download that between now and the time it's due. I didn't get around to that on Wednesday, but I'll do it right after class today. Today I want to really finish up talking about quantum mechanics and sort of talk about what the competing modern interpretations are of quantum mechanics, because there's still, while there's no disagreement that quantum mechanics works and does what it's supposed to do, there's still some disagreement even among physicists about what quantum mechanics means and how to interpret, for example, Schrodinger's equation and this entity called the wave function. So we're going to talk about that today. We're going to talk about a famous thought experiment by Schrödinger designed to sort of explore the meaning of quantum mechanics. Just to review what we talked about last time, we decided that since the uncertainty principle puts a fundamental limit on sort of the knowability of quantities in physics, more specifically, it doesn't allow us to talk about the exact velocities and the exact positions of objects the way classical physics always assumed that we could. That it is not possible to consider a trajectory the fundamental entity of physics anymore. What classical physics was all about was calculating a trajectory given a known set of conditions. The way Newton did it was to know the velocity and the position of something exactly, and you plot the trajectory based on what forces are acting on the object. Post-Newton, in the 1700s, physicists developed a new way of thinking about how to calculate a trajectory. It turns out that knowing the force on an object at every point in space is actually quite difficult. For example, if you think about the Earth going around the Sun, sometimes it's closer to the Sun, and sometimes it's further from the Sun, and sometimes it's moving fast, and sometimes it's moving slow. And because its distance from the Sun is changing, the force is always changing. And that's actually a fairly complicated problem. In the 1700s, people like Lagrange and Hamilton came up with a way to calculate trajectories based just on the energy, the total energy of the system, without having to know the force on it every time. It turns out that there's a different Heisenberg uncertainty principle, or a different expression for Heisenberg's uncertainty principle. We said that the Heisenberg uncertainty principle is a trade-off between how well we know the position and how well we know the momentum or velocity of a body. The product of those two uncertainties is always greater than some minimum. There's another uncertainty principle, which is really the same uncertainty principle. It can be shown that these two are equivalent, but it's another way to think about it, that relates energy and time. That is, how certain we are about the energy of a system depends on how long of a time we're allowed to measure that energy. And that the energy of a system can actually vary over very, very short times. And so there's a trade-off between how long we observe a system and how well we can know its energy. And that makes this sort of calculation from the 1700s impossible. If we can't know the exact energy at any given time, we can't know exactly how that trajectory will unfold in space. So the idea of a trajectory falls apart. And what we're left with in the modern interpretation is probability. That rather than plotting the path of an electron through space, what we get when we solve the Schrödinger equation is that we wind up with a set of probabilities for regions in space where we're likely to find an electron and regions in space where we're unlikely to find an electron. And when we get these sort of graphs printed out by the atom in a box program, which is really all that program is doing is graphing solutions to the Schrödinger equation. we're getting a picture of the probability distribution of the electron in space. So this thing, psi, the wave function, or more particularly psi squared, the square of the wave function, in modern quantum mechanics, we interpret as the probability of finding the electron with a particular value of some quantity. In this case, we're talking about position. So this is the wave function of the electron in space, in position space. But you can also write a wave function for spin, a wave function for momentum, and get a more abstract picture of probabilities in abstract spaces rather than physical spaces. But here we're talking about, in this course, we're mostly interested in where is the electron. So what this picture means is that we're very likely to find an electron there, and we're very unlikely to find an electron there. And on the borders, we might find the electron there every once in a while, but maybe not very often. So the Schrödinger equation, which we saw on the board, and it's not terribly instructive, I don't think, for any of us to see it again. It was something delta squared psi plus v psi equals this of n psi, and this is either h bar over 2 or h bar over 2 pi or h bar over something. I can't remember. It doesn't really matter for our purposes here. What's important is that it's a differential equation that gives us a wave in space as its solution. And this wave will have different characteristics of energy for each n equals 1, n equals 2, n equals 3. So when you solve the Schrödinger equation, you're finding a bunch of wave functions. And each of those wave functions will have a different shape. And we saw the shape of some of them when we looked at the atom in a box program, or something that sort of look like this. A little donut here, a little donut there. Okay, so these solutions can actually be very complicated. Nobody really solves the Schrödinger equation for anything more complicated than a hydrogen atom. Throw another electron in there and try to solve the Schrödinger equation for a helium atom, where, remember, this V was the potential or the force experienced by the electron. The fact that there's 2 electrons in there, each exerting a force on the other one, makes it basically an unsolvable problem. So when you take an undergraduate quantum course, you tend to do the hydrogen atom in class as a group, and then for homework you get simpler problems than the hydrogen atom to solve. My midterm exam in my undergraduate quantum class was to solve the Schrödinger equation for a 2-dimensional hydrogen atom, a flat hydrogen atom. So if you lived in a 2-dimensional universe, what would the energy levels of a hydrogen atom be? So you can get simpler than the hydrogen atom and get an equation you can solve. Anything much more complicated than the hydrogen atom, finding a solution is really mathematically difficult, if not impossible. What you can do is find approximate solutions, and there's a whole field of physics and mathematics called perturbation theory, which allows you to find approximate solutions to equations that you can't find an exact solution to. And that's not anything that we really care about here, because it's sort of beyond the scope of this course. But what we care about is the meaning of this thing called a wave function. That when I graph this thing psi or psi squared, I get a set of probabilities in space, and maybe I get for psi 1, psi 2, a particular physical system, I might get different wave functions at different energies. The question is, what is this? And what this represents are different probability distributions. The question is, what do these probability distributions represent? How do we think about them? And the fact that when you're doing quantum mechanics, when you're not observing the system, you have to treat the system as being a sum of its possible states. And this is something that we call superposition. Means that we have to think about what it means to say that a particular system, and let's stop talking in the abstract. Let's think about something concrete. Suppose we have a box with an electron in it. Okay? That's our physical system. We build a tiny little box and we put an electron inside. and we solve the Schrödinger equation and say these are the different wave functions that describe where in the box we'll find the electron. When I'm not making an observation, what I do is say that the wave function of that electron is equal to the sum of 1, 2, 3, the possible states that the electron could be in. And it's only when I make a measurement, okay, with my giant floating eyeball of physics, okay, that I decide, or I discover, or I cause, depending on how we interpret it, one of these wave functions to be the one that I observe. And remember that this floating eyeball of physics is not a passive event. It involves somehow interacting with that electron so as to make that observation. So when I make the observation, I find the electron in one of its states. But before I make the observation, I have to consider all the possibilities.
I have a question. Since you can't observe it when it's in the other state, how do they know that it's actually in that state?
Well, I will show you a concrete example of that in about 20 minutes, okay? The question is, do we really have to do that? Do we really have to consider it to be in a superposition of states? You know what, why don't I do that example now? Because it actually flows very nicely out of what we just talked about. The example I gave last time is this electron spin example, where we have two electrons that are prepared in such a way that we know their spins are opposite. So I have some event here that makes two electrons, or causes two electrons to fly out into the world. And because this thing called angular momentum is conserved, whichever way one electron is spinning, the other electron has to be spinning the other way. So one electron is spinning spin up, and one electron is spinning spin down. Remember, what we mean by up and down is sort of which direction the north pole of that electron is facing. And these electrons go out in this direction, and I'm going to observe them somehow here and here. Now there are two possibilities. Let's label the electrons 1 and 2. This really comes down to the fact, and when we're talking about particles in quantum mechanics, the real problem is you can't label an electron. You can't put a sticker on it and say this is electron 1 and this is electron 2, because all electrons are identical. There's no way to tell them apart. But this observer, before he or she makes the observation, has to consider the wave function of the electron approaching him to be a sum of, we'll write it 1 up. Well, we're only observing 1, so I'll write it like this. Up plus down. And you know what? I'll even put the probabilities in there. Because as far as I know, in this experiment, there's a 50-50 chance that the electron I get is spin up or spin down. So the wave function is 1/2. Instead of writing the arrows, why don't I just write up? 1/2 up plus 1/2 down. And these little brackets are just a notation that physicists use to indicate parts of the wave function. And so the electron gets here, and I make a measurement. How do I make a measurement? Basically, I put the electron in a magnetic field, and I discover from its spin whether it's lined up with it or lined up against it. When I do that, I find that it's, well, it's not magnetic field, it's angular momentum. I find a particular value, that it's h bar over 2. So it's spin up, okay, not negative h bar over 2.
How does the magnetic field not change the spin?
Well, it does. I mean, it could. If it were in the wrong direction, the spin would flip, and that's how we knew it was in the other direction, right? So that's the whole business about when I make the measurement, I actually change it. So I know what it is, but I don't know what it is. I know what it was, but I don't know what it is now, right? So there's no way to measure that spin without interacting with it via a magnetic field, somehow. Now, you may say, well, there are two things that are important here. One is that I know now another piece of information, which is that the angular momentum of the other one is minus h bar over 2. So I now know a fact about something that's happening way over here. Okay? This is something that troubles a lot of people about quantum mechanics, which is that these 2 points could be very, very far apart. Okay? This experiment could have been set up on Jupiter, and this could be on the Earth, and this could be on Saturn. Which means that the second I make this measurement, I know something about something that's happening on Saturn instantaneously. Now, why is that a problem? That's a problem because the theory of relativity says information shouldn't be able to travel through the universe at faster than the speed of light. And it takes light something like, well, it takes about about a half hour to get to Jupiter. Probably takes about an hour and a half for light to get from the Earth to Saturn. So I shouldn't ever be able to know what's happening on Saturn now. I can only know what happened on Saturn an hour and a half ago. Right? If somebody were to call me on the phone from Saturn, I would be hearing the thing they said an hour and a half ago because the signal from their cell phone would take an hour and a half to get from Saturn to the Earth. The fact that my measurement of the electron spin, the spin of electron 1, gives me the spin of electron 2 as being down, is something that's often referred to as non-locality. Quantum mechanics is non-local in the sense that when 2 particles are related to one another, and the word that's used to describe the relationship between these 2 particles is entangled, because we know because they were once in the same point in space, some property of them is correlated. In this case, they're spins. We know they have to be opposite. Because these particles are entangled, I will always know something about one of them if I measure that property of the other one. Assuming that property hasn't been changed between Jupiter and the Earth, which is a pretty big assumption, actually. Now, non-locality, you go through sort of stages of how you deal with non-locality. The first is probably not seeing that it's a big deal. And saying, well, how is this different from the example I gave in class, where I take a dollar bill, and I rip it in half, and I send one half to this person and one half to the other. And when I open my envelope over here and discover that I have the left half of the bill, I know that this person has the right half of the bill. Okay, so I know something about something that's happened on Saturn instantaneously the second I open that envelope. The situation in quantum mechanics is a little bit different, because in quantum mechanics, we have to believe that something has changed. What has changed is the wave function. The wave function has gone from 1/2 up plus 1/2 down to just up. Meaning the wave function here has changed from, wave function 2 was always 1/2 down plus 1/2 up, meaning if 1 was up, 2 is down, and vice versa. And now that wave function has changed to just down. Here, nothing ever changes, right? The second I put the left half of the bill in the envelope, it's always the left half of the bill as it passes the asteroid belt, and then Mars, and then the Moon, and then the Earth. It was always the left half. And the right half of the bill was always the right half as it traveled through the solar system to Saturn. Here, the wave function of the electron was a superposition of 1 and 2, and a superposition of up and down in both directions, until I measure it, and then it changes to something else. It's this change of the wave function that is the troubling part of quantum mechanics. The wave function, which is the only mathematical description of a particle we have, changes when I observe it. This is sometimes referred to as the collapse of the wave function. The old wave function is no more good because we know that it's not down because we made the measurement. And now there's a new wave function that describes the fact that we made the measurement. And now we know the spin of that particle. At least we know it at an instant in time. The second this wave function collapses, this one collapses too. And it's the collapse of the wave function that's non-local. Okay? That when I collapse the wave function of particle 1, the wave function of particle 2 also collapses into a definite answer rather than a sum of two probabilities. The first thing I need to prove to you is that we have to think about the electron this way. That we can't just say, well, I measured it to be up, that means it was up all along. And I just hadn't measured it yet, just like the dollar bill in the envelope. Right? And here, it was down all along. And so measuring it to be up over here didn't change anything about this electron. It was always down and I just didn't know it. That's one interpretation of quantum mechanics called a hidden variable theory, which is very, very difficult to justify. And I'll give you as concrete an example as I can give you without a billion-dollar physics lab, that we have to think of particles we're not observing that way. And we're going to use light instead of electrons. It's very much the same experiment, except our two observers, rather than being in opposite directions, are in the same direction. And instead of using the spin of an electron, we're going to use the polarization of light. And so in order to understand the experiment, we have to understand what polarization of light is, which is a pretty simple idea. Remember when I talked about light being a wave, I said that you can draw this electric field that changes over time. And that electric field creates a magnetic field that also changes over time. And it's this changing electric and magnetic field in an empty space. They're at right angles to one another. That is what we think of as light. And remember what a field is. A field is an abstract mathematical notion, but it tells us the direction that the electrical force would be on a particle if we put a particle there. So here the particle would feel a tiny force this way, here it would feel a big force that way, here it would feel a force that way. And the wave is a wave of electricity and magnetism that if we sort of connect the dots, right, there's an electric field that varies in space, and there's a magnetic field that varies in space at right angles to that. We can almost always ignore the magnetic field because magnetic fields are a factor of speed of light weaker than electric field. So the magnetic field in a light beam is 10 million times weaker than the electric field. The electric field is the thing that interacts with matter for the most part. Now, when you have a beam of light traveling from a light bulb to your eye, the direction that this electric field oscillates can be in any direction. It can be this way, it can be this way, it can be this way. In general, light that's coming at you, the direction of this electric field is all over the place. And so some of the light coming at you, the electric field is going up and down, up and down, up and down like this. Some of it's going left and right, left and right, left and right like this. Some of it's going like that. The direction of this electric field is called the polarization. And most light around us is uniformly polarized in all different directions. So the light coming from these light bulbs, there's just as much going this way as there is this way as there is this way. So if we look at it on end, okay, some of the electric field is going like this, some of it's going like this, some of it's going like that, some of it's going like that. But we can artificially, using various materials, select out part of that light and block it. And that's called a polarizing filter. If you've got a pair of polarizing sunglasses, the reason to wear those is that it blocks out light with a certain polarization. And the polarization that you want to block out is this way. Because when light bounces off of things, like a road or a table or the surface of a body of water, the object blocks most of the light that's polarized this way, and so the light that's reflected is polarized this way. So if I wear glasses that block the light polarized this way, it eliminates the glare off of the surface. That's why you wear them when you're driving. That's why you wear them when you're fishing. If you wear polarized glasses when you go fishing, you can see the fish under the water because it blocks the glare off the surface of the water. I have some polarizing filters that I've stuck to great big arrows. I did this morning because I realized it's hard to tell from back there which direction I'm holding the polarizer. So the arrow shows you the direction that the polarizer lets through, I think. I think that's the way I set it up. I need to find some glare. Yes, okay? So it's set up that the arrow is the direction that it lets through, and it blocks light of the other polarization. It's really interesting to look at an LCD projector through a polarizer. Doing these demos was much easier back in the day of overhead projectors because they just give you white, unpolarized light. You can't use a projector because the light coming through a projector is actually already polarized. So what we're looking at is the square here, and the light that's coming through the polarizer. And you'll see, it's all one color. That's not good. I need white. So let me get some white light up here. Just open a random window. That's interesting. Blank web page. So, if we look at the white light coming through the square and watch it when I turn this. Does everybody see that? And the reason for that is the red, green, and blue light coming through the projector is coming out at different polarizations. The red light's polarized one way, the green light's polarized another way, the blue light's polarized another way. So when I block them in turn, I get the complementary color, okay, with the red removed, and with the yellow removed, and with the blue removed. So this light is not really good for us. So we need light that's randomly polarized. I discovered this the first time when I was sitting in my office looking at my laptop and got ready to leave and put my sunglasses on. They were polarized sunglasses, and my laptop screen went completely black because the laptop light was polarized. And you can see that with this polarizing filter. If you turn it this way, the screen of a laptop goes, actually, to you, okay? We just look at the laptop through the square. If I turn it like this, I get all the light. If I turn it like that, okay, it blocks all the light. So we don't notice polarization because most of the light that comes at us in the world is randomly polarized. Our eyes do not have polarizing filters in them, so we cannot sense polarized light. We can't tell the difference between polarized and unpolarized light. There are animals in the animal kingdom, there are insects, they actually tell the difference between polarized light and non-polarized light. I think there's some birds that can tell the difference between polarized light and non-polarized light, which helps, for example, in orienting yourself in the sky. For example, the sky opposite the sun, the light is slightly more polarized than others, and there are some plants, I think, that slightly polarized light to give certain animals, flowers and whatnot. Anyway, so when I put this filter in front of light, I'm letting through only one of the polarizations. So when I put this filter through light, I'm letting through light only polarized this way. By the way, the way it works is just by using plastic that has really, really long molecules, and you use it with all the molecules lined up in one direction. If I use a plastic that's got big, long molecules like this, and we think about the electrons in that molecule, the electrons are free to go from atom to atom this way, but they are not free to jump out of the molecule that way. So when an electric field comes by this way, it moves the atoms around, and those electrons take energy away from that light wave, and they block it. So if the atoms are lined up this way, it will block light polarized like this, and it will let light through polarized like this. You can think of it as, if you want to think about it even more schematically, you can think of it as trying to walk through a bunch of really narrow columns, right, swinging a stick like this. If there are a bunch of narrow columns, and I try to walk through swinging my stick like this, I'm not going to be able to get through because it's going to block them. But if I swing my stick like this, I'll be able to get through the columns. Okay, so a polarizer blocks light of one polarization and it lets through light of another polarization. Which means if I take two polarizers and cross them like this, they should block all the light, right? This blocks all the light going this way, and some of the light going this way, and some of the light going this way. This one will block all the light going this way, and also some of the 45. And between the two of them, if I hold them like this, they should block everything. Okay? So the first thing we should do is test that. So there's my laser, which is my light source. I'm going to set up one of my polarizers horizontally. In a few minutes, I think I'll need an extra hand to do this, but for now, I can probably manage just me. So I'm going to set up this polarizer horizontally. Okay? So notice what happens to the laser light. It gets a little bit dimmer, but not much. Okay? Which means that the laser light, well, it gets much dimmer if I block the whole thing. I got to make sure it goes all the way through the polarizer. Laser light is unpolarized. There's just as much horizontal as vertical polarized light. So when I put the filter in front of it, it blocks about half the light, which is what we would expect. Now, if I take my second polarizer, let me come over here. I've got to find the light. There it is. Okay. So the first thing I want to do is set it up in the same direction as that polarizer. If this polarizer is polarizing the light this way, and I put it in front of this, what should happen? Nothing, right? Because it's already polarized that way. So when I put this in front of it, okay, it still has pretty much the same amount of light. It's a little dimmer because this stuff is gray, not transparent, so it absorbs a little of the light, but polarization-wise, pretty much all of it gets through. Now watch what happens if I turn it. Okay, so here's horizontal. Oops. Okay, I got to make sure I keep the light through it the whole time. Horizontal. Vertical. Okay, it's gone. Horizontal. On, off, on, off. Okay? Yeah, it's basically like a valve for light. So two cross polarizers will block all the light. And I can think of what I'm doing quantum mechanically here as making an observation. We can think of this as a device for measuring whether the light is horizontally or vertically polarized, right? Here's the light coming through. Is it polarized that way? No. Is it polarized this way? Yes. No. Yes. No. Yes. So we can think of this as an observation. Now, if we think about this beam of light quantum mechanically, I have prepared the light in some state. So here's my laser. And the state of that light, if we want to write it as a wave function, is going to be some sum of, we'll call it vertical and horizontal. Until I know whether it's horizontally or vertically polarized, if I'm the observer here, I have to consider it to be a sum of those two. When I make my observation with my second polarizing filter, and we find the light again, okay, there it is. When I make my observation, I determine that it's vertically polarized. When my polarizer is vertical, it blocks it. Okay, block. And so now I know that the wave function of the light is horizontal. Okay, so if we take this wave function business seriously, when I make my observation, the wave function changes. Now, how do I know that it wasn't horizontal all along? Common sense tells us that I prepared the light horizontal here. This observer here just doesn't know it. What I'm going to do is put a second observer here to verify that the light is in fact polarized the way I say it was. Okay. And that observer, where's my other thing, is going to put their polarizer in at a 45-degree angle. So here it is, like this, here it is like that. Okay? Vertical. Horizontal. Oh, did I put this one in backwards, didn't I? Damn it. Your reflection. That should be letting it through, shouldn't it? I taped the thing on wrong. Well, it doesn't matter because we're going to put this one at a 45-degree angle. So what I need someone to do is to hold. Chuck, can you do this for me? It helps to stand where you can see that dot. Okay, and just hold it vertically so we're blocking all the light. Okay, so there it is horizontally, there it is vertically, blocking all the light. Okay, now you keep that still. And what I'm going to do is I'm going to be a second observer, and I'm going to make an observation of the polarization in between all the lights out. Here and here. Now, if I measure the polarization horizontally, I shouldn't affect the beam of light, right? Because it's coming horizontal. I measure it horizontal. And so let me find my beam, put it through the thing. Watch the screen. Okay? You shouldn't see anything change, right? Horizontal. If I change it to vertical, I shouldn't see anything change either, right? Now I should just block all the light here. Okay? All the light is still blocked. Suppose I make an indeterminate measurement at a 45-degree angle. Right? If this is blocking all the horizontally polarized light, this is blocking all the vertically polarized light. Should it make any difference if I measure its diagonal polarization here? No, because all the light's getting blocked, right? Okay, so I'm going to put this in here diagonally. Now watch the screen. Okay? 2 polarizers block all the light. 3 polarizers block not all the light. Okay? Watch it again. 2 polarizers are blocking all of it. I put a polarizer in between those 2, and I get more light with 3 than I got with 2.
Is it because of refraction?
No, it's not because of refraction. Okay? Think about this for a minute. 2 pieces of plastic are blocking all the light. 3 pieces of plastic are not blocking all the light. Okay?
Is it because with each measurement we're changing the
Yes. It's because by measuring the light here, I am changing something about the light here. If we think about it in terms of the wave function, just go ahead and turn them all back on if you could. Thanks. If I set up the wave function with a polarization in this direction, then the wave function is some combination of up and down. What was I calling them? Horizontal and vertical. What I'm measuring here, by measuring the polarization horizontally and vertical, is the polarization on that axis. So the relevant measurement for me is the polarization horizontal or vertical? What this observer does here, though, is messes up the experiment by measuring something completely different. Here, I'm asking the question, is the wave function this or that? So the wave function for him is 1/2 45 degrees plus 1/2 minus 45 degrees. When I make my observation of the wave function here, I select out one of these possibilities that then goes on to this person. And 45 degrees is a combination of horizontal and vertical. Okay? So I have changed the question here. And changing the question we're asking about the light, quantum mechanically speaking, changes the wave function of that light. Okay? I've gone from asking, is it this or this, to asking, is it this or this? That observation, and remember, that observation is not passive. It involves me putting something in the way of the light. changes the light, and it changes the wave function of that light to something different. If I assume once it's horizontal, it's always horizontal, I get the wrong answer. If I assume once I've polarized this light horizontally, it's always going to be horizontal from there to here, I cannot explain why putting something here changes what shows up on the screen. In between the observations, I always have to consider the light to be in superposition. Okay? I always have to consider it to be a sum of two possibilities. If I ever assume that I know it's one thing, I can get the wrong answer, okay, by making an observation that's of something that's not orthogonal to those two. That's not a yes or no question. It's a question along another axis, or it's a question about another property of that particle. I'm not allowed to say that I know the wave function here, so I know it forever. And so in some real sense, particles, when they are in between observations, exist in the state of superposition. You have to consider them to be a sum of both possible outcomes until you make the measurement. This led Schrödinger to a very famous thought experiment, where he asked the question, where do we stop thinking about things quantum mechanically and start thinking about them classically? And it's based on taking a single quantum system. Okay? The system that Schrödinger imagines is a radioactive atom, say a single atom of uranium or cobalt-60 or something radioactive, that can decay by emitting an electron, let's say. Now, one of the things we learned in the 20s and 30s, and something we'll make, in the 40s, I guess, and something we will make much of after break, is that radioactive decay is a purely random process. That if I have an atom of uranium, a single uranium atom with a radioactive nucleus, that nucleus might decay in 5 minutes, it might decay in 5 years, it might decay in 5 million years. I have no idea when it will go. Okay? It is literally a ticking time bomb. What do I know? I know if I have 1 million of them, this amount will decay after 5 minutes, and this amount will decay after 5 years, and this amount will decay after 5 million years. So I know the probability it will decay after a certain amount of time. But given one atom, I have no way of knowing when it will decay. Which means, while I'm not looking at it, the wave function of the atom is some sum of decayed plus not decayed. And these don't have to be halves. This could be 99% and 1%, depending on how long it's been sitting there. And I put this atom in a box. And I point a Geiger counter at it. That will record whether or not it decayed. Okay. And I connect that Geiger counter to a hammer. And I place below that hammer a bottle of poison. And I place this whole physical system inside of a box. With a cat. So this experiment is called the Schrodinger's Cat Experiment. No cats were harmed in the invention of the Schrodinger's Cat Experiment. This is a thought experiment. Okay? It's something we do in our heads to think about the implication of quantum mechanics. Okay? Nobody's actually suggesting we poison any cats in the name of quantum mechanics. But the outcome of this experiment is determined by the decay of this atom. If the atom decays, the Geiger counter clicks, the hammer drops, the poison breaks, the cat dies. So what we've done is we've connected a macroscopic event to a microscopic event. What's the point? The point is, if we close the box so that we're not allowed to look in it, quantum mechanics says, while we're not observing the atom, the wave function of that atom must be treated as a superposition of its two possible states. In this case, the state where the atom is decayed, plus the state where it's not decayed. If there was no Geiger counter in the box, we wouldn't know until we opened the box whether that was still a uranium atom or if it had decayed into something else. But there is a Geiger counter, and the state of the Geiger counter is directly determined by the state of the atom. So the Geiger counter has either clicked or it has not clicked. And the state of that Geiger counter, as a whole, is uniquely determined by the state of the uranium atom. If the uranium atom went off, it clicked. If the uranium atom hasn't gone off, it hasn't clicked. Therefore, the state of the hammer equals 1/2 dropped plus 1/2 not dropped. State of the poison is 1/2 broken plus 1/2 not broken. And everybody sees where this is going. The quantum mechanical state of the cat is a superposition of the state dead and the state alive. And there is a direct causal chain from one of these states to the next. And the tricky thing to get out of all these discussions of the Schrodinger's cat thought experiment is what Schrödinger was getting at. There's lots of talk about the Schrödinger cat experiment, and is one of the places where people get themselves confused about what quantum mechanics is all about. Especially if you read some of these books like What the Bleak Do We Know? Stephen Hawking's famous comment about the Schrödinger cat experiment is whenever anyone mentions Schrödinger's cat, I reach for my gun, because it can lead to so many unproductive, ridiculous conversations. What was Schrödinger's point? Schrödinger's point is that quantum mechanics demands that we talk about atoms in this way. Quantum mechanics requires us to treat unobserved quantum entities, electrons, photons, atoms, whatever subatomic particles we're dealing with, as being in a superposition of states when we're not observing. Common sense tells us that if I've got a box with a cat in it, that cat is not in a state of 50% dead and 50% alive. That cat is one of these things or another. Okay? Either it's a dead cat or it's an alive cat. We might not know it until we open the box, but all of our macroscopic experience tells us that even before we open the box, it is either dead or alive. That things that we're not looking at don't exist in this sort of 50-50 state until we look at them. The moon is not half there and half not there because we can't see it right now because it's on the other side of the earth. So the question then is, how do we treat this wave function? Is it real or is it some sort of side effect of quantum theory? What does this wave function mean? And if it is a real thing, and most physicists believe that it is to some extent a real thing, when do we stop, when in this chain of events do we stop thinking about things quantum mechanically and start thinking about them classically? When do things stop being a sum of probabilities and start being one reality? Okay. One can argue various points in the chain that the observation has been made. One can argue that, one way to think about it is, when is the observation made? Okay? The naive, humanocentric way to think about it is, the observation is not made until somebody opens the box, right? I'm the physicist. I'm the one that wrote the equations. I make the observation when I open the box and see either a dead cat or a live cat. Right? That the cat is basically my Geiger counter. The cat is telling me something about the atom. One could argue that the cat is a pretty good observer in this situation too. Okay? The cat either smells poison or doesn't smell poison, and either dies or doesn't die. So in some sense, the cat has observed whether or not the atom has decayed or not. One could even say that the Geiger counter is the thing that does the observing. When that needle on the Geiger counter moves and the speaker makes a little clicking sound, this decay has been observed. There's even a bigger version of the Schrodinger's Cat Experiment called Wigner's Friend, where Dr. Wigner, who's a physicist who's a contemporary of Schrödinger, is the one in the room doing the experiment on Schrodinger's cat, the one who opens the box. But we seal Wigner in his lab and close the door, and Wigner's friend stands outside the door. And so Wigner's friend, when considering the quantum mechanical state of the lab, has to treat Wigner, W-I-G-N-E-R, as in a state of 1/2 saw a dead cat plus 1/2 saw a living cat. Okay, and this quickly just gets ridiculous, right? I mean, you can put everybody in a room until everyone becomes their own observer, and the whole rest of the world exists as probabilities until I, me, myself, make an observation of it, which is basically the philosophical position of solipsism, right? The only reality that exists is my perception. Most physicists think that's a load of crap, and that's not what quantum mechanics is telling us, right? Quantum mechanics is not telling us that the universe only exists throughout our observations. What it's telling us is that there's a disconnect between the way we have to treat macroscopic events and the way we have to treat microscopic events. That macroscopic reality seems to have one answer to every question. Right? Microscopic reality seems to have a set of probabilities that are not actualized until an interaction takes place. To some extent, the whole problem with quantum mechanics comes from facing the disconnect between the observer and the observed. And this is where the word reality, which is a word that I don't think physicists should ever use, but this is why it comes into quantum mechanics. Because when I talk about making an observation of the world, in science it's always been assumed that I can separate myself from that thing I'm observing. That here is a ball rolling down a plane, and I'm making measurements of it, and it's doing the same thing during the experiment with me measuring it that it would be doing if I weren't there. That when I set up a physical system, that the observer is not affecting the physical system, and I'm measuring what's really happening in nature. Quantum mechanics takes us down to a scale where we can't assume that anymore. We can't assume that when I set up a physical system and let it do whatever it does, that my observation of it is not affecting it. My observation is always tied up with it in a real, measurable, calculable, unavoidable way. So the question then is, how are we to think about quantum mechanics as a theory about the way the world works? One way to divide the question is a division that's really a fundamental division in the philosophy of science, between realism and instrumentalism. We talked about this a little bit in the Science and Religion course last semester, and we will talk about it even more in the What is Science course next semester, which is a 3,000 level sort of philosophy and history of science course that I'm teaching in the fall. The question of realism versus instrumentalism comes down to the question of what scientific theories are. What are they about and what do they do? A realist thinks that what a scientific theory is a description of the real universe. So if I say everything is made of atoms and atoms contain electrons, that thing, that part of the theory, electron, corresponds to some real object in the real. That's a realist. An instrumentalist says that what a scientific theory is a tool for making predictions about the world. It has nothing to do with reality in the sense of capital R, thing that exists outside of our brains. It is all about matching predictions with observations. So what is an electron to an instrumentalist? An electron is an idea that helps us explain what happens when I flip the light switch on. Okay? What happens when I rub a balloon on my head? Right? What happens when I rub a balloon on my head? My hair stands up and I can stick the balloon to the wall. Right? I explain that based on this idea of electrons, little tiny chunks of electrical charge that exist on the outside of atoms that I can rub off my hair onto the balloon and then stick it to the wall. That does not necessitate there being any such thing as an electron in the real world. An instrumentalist says scientific theories are not about the real world. They're only tools for making predictions about the real world. Or, I don't know, instrumentalists might not even use the word real if they can avoid it. So, the question is whether we think quantum mechanics is properly about reality, capital R, or whether it's a tool. The big debate between realism and instrumentalism, that is sort of the most famous one in the history of science, deals with Copernicus versus Ptolemy. The question of whether or not the Earth goes around the Sun or the Sun goes around the Earth. From ancient times through the Middle Ages, people assumed the Earth was stationary and the Sun went around the Earth. And then Copernicus comes along and says, the whole thing makes a lot more sense if we put the Sun in the middle, we make the Earth go around the Sun, and explain the motions, the fact that the Sun rises and sets by the fact that the Earth is spinning around, not vice versa. And in 1550, when Copernicus published this, there was really no way to tell the difference. There's no way to tell which of these theories was right. They were both sort of equally did a good job of explaining what we see when we look up in the sky. And when Copernicus published his work on the revolutions of the heavenly spheres, the person who published it put a disclaimer, basically, on the first page of the work, saying that this treatise is proposing a convenient way to calculate the positions of the planets, but it makes no claims to the truth. Meaning that we can consider the Earth to be stationary and the Sun to be moving, or the Sun to be stationary and the Earth to be moving. Nobody knows, because the only way that we can learn the truth about anything is from God, according to this guy, who's a Lutheran theologian. Both are equally good tools for figuring out what's happening in the solar system. Nowadays, we would dispute that, right? We would say there is a right answer to that question. Either the Earth is stationary or the Sun is stationary, and one of those answers is real, and the other one is, you might be able to get the right answer by using that model, but the model is wrong. And I wouldn't disagree with that, and I don't think most scientists would disagree with that. But when you remove yourself from the phenomena that you're observing by layers and layers of instruments and layers of observations and layers of theories, then the reality of your thing that you're claiming to exist as part of your theory gets sort of thinner and thinner and thinner and thinner. And so while we say that atoms are real and electrons are real, in some sense what we mean is the idea of electrons does a really good job of explaining everything we observe about atoms being rubbed against one another and power plants making electricity that flows through wires and the structure of chemical reactions and how chemicals two elements combine with one another. But nobody's ever seen an electron, so we have to be careful about the way we regard them as a entity in our theories. A realist would say, of course there are electrons. Of course electrons are real. That's why the theory works. If they weren't real, why would a theory that includes electrons explain the real world? An instrumentalist would say, all we know is that the idea of electrons explains the observations that we have made so far. There's no way of getting in touch with that sort of object except through the theory. So if we apply that to this idea of a wave function, how do we regard the wave function? A realist would say the wave function is some sort of real description of what an electron does. This mathematical set of probabilities is, in some sense, a real part of the electron's behavior. And when you're measuring the position of an electron, you're measuring something about this wave function, which is a real thing. An instrumentalist would say all quantum mechanics is a tool for telling us when I have a bunch of atoms, what will they do? If I have a tube full of hydrogen and I run some electricity through it, what kind of light will come out? So the wave function need not be a real thing. It is just a mathematical construct. Does it matter? It matters a little bit, because if we talk about this idea of non-locality, it's kind of important to us whether or not the thing we've changed is a real object or a mathematical construct. If I've got this two-electron experiment, and I prepare my electrons such that I know they have opposite spins as one another, and I send them off into the universe, and I have to treat them as being a sum of up and down, an equivalent sum of down and up. Until I observe them. And when I make the observation, I change this wave function to, let's say it was up. And I immediately change this wave function to down. It kind of matters whether the wave function is a real thing or a mathematical construct, right? If it's a mathematical construct, the fact that I've changed a mathematical construct here and here instantaneously doesn't matter, because a mathematical construct is not a real thing, right? A mathematical construct is just something abstract. Okay? If I say that the probability of rolling a 7 with 2 dice is represented by this diagram, where there are 6 ways to roll a 7 and only 1 way to roll a 12, and then I roll 2 dice and I get an 8. Okay. I have not changed any. This thing doesn't change, right? This is just a mathematical description of what might happen when I roll the dice. It's not a physical entity with a reality independent of the dice. It is just a mathematical description. But if the wave function is the electron, and when I make a measurement of it, I'm changing some physical thing here and here simultaneously, then that kind of is a real problem. Because it seems like I've caused something to happen somewhere else in the universe instantaneously. And physics doesn't like that. Physics doesn't like causes to be instantaneous. Especially Einstein. Einstein likes causes to be happening at the speed of light maximum. So the question of how we regard this collapse of the wave function is tied to whether or not we think the wave function is a real thing. One interpretation of quantum mechanics is called the statistical ensemble interpretation, which just says the wave function is no different than the histogram of rolling dice. That a wave function is just a probability distribution that is a mathematical description of what would happen if we rolled 1,000,000 dice. We would get lots of 7s and a few 2s and a few 12s, and the distribution would look like this. The statistical interpretation of quantum mechanics says that what a wave function is a description of what would happen if I did this 1,000,000 times or 1,000,000,000 times with 1,000,000 electrons or 1,000,000,000 electrons. So it relegates the role of the wave function to purely a tool. Okay? Now, that's not the most popular interpretation of quantum mechanics. The most popular interpretation of quantum mechanics is probably the Copenhagen interpretation, which says that the wave function is a real thing. And that when you make an observation, that wave function collapses from a probability to a definite answer. So this collapse is a real thing that happens. When I make an observation, I change the wave function from one thing to another. But this is not a causal relationship. Okay? It's just a fact about life that wave functions are not local the way positions and velocities and temperatures and energies are local. The wave function of this particle encompasses the wave function of that particle no matter how far away it is, and that's just a fact of life we have to deal with. Okay? Quantum mechanics is non-local. And when we make an observation, we are selecting one of those possibilities as being the real one, and all the other ones go away. The question of where this collapse happens varies from physicist to physicist. Okay? If we think about Schrodinger's cat, some say it happens when the Geiger counter clicks. Some say it happens when the cat dies. Some say it doesn't happen until someone opens the box. And some would say it does not. A very small number would say that it does not ever happen. That the probabilities just get smaller and smaller and smaller and smaller. But we really live in a world of sort of a coherent interference between a bunch of possibilities all the time. And that what we perceive as reality is just that one of those possibilities is a very, very small, large probability, and all the other ones are very, very, very small. And that is reality, despite the fact that it seems like reality only has one answer all the time. There are lots of other interpretations of quantum mechanics. I'm only going to talk about a couple. When you do your quantum weirdness paper, you can do some research. If you Wikipedia interpretations of quantum mechanics, you'll get a big list of them, some of which you will understand, some of which you will not. But it's not a bad place to start. There's one interpretation of quantum mechanics that gets a lot of airplay, I think simply because of its weirdness, called the many worlds interpretation of quantum mechanics, which says that every time we make an observation, for example, here comes the electron, I'm going to measure whether it's up or down. It's got a 50-50 chance of being up or down. When I make that observation, the universe splits into two parallel universes. One in which I measured the electron spin up, the other in which I measure the electron spin down. Okay. Many worlds.
But then there's just like an infinite amount of universes forever and ever, right?
Yes.
That means anytime there's like a matter of probability, there's a new world.
Yes. Which is a kind of an unwieldy theory, right? When you start postulating an exponentially growing number of universes parallel to our own, it begins to be a bit of a silly theory. I think it's kind of a cop-out. I think most physicists think it's kind of a cop-out. The problem it solves is that the wave functions never need to collapse. Okay? All that happens is that the universe splits into two possibilities with the two different answers. And so nothing about the wave function has to change. Basically what you're writing is the wave function of the universe that keeps splitting and splitting and splitting and splitting every time there's a quantum decision. So there's a universe where you missed the train this morning and didn't make it to class. There's a universe where you had cornflakes instead of Rice Krispies for breakfast. There's an infinite number of universes for every sort of possible decision, quote unquote, that could be made in the universe. my problem with the many worlds interpretation of quantum physics is that anything that postulates the existence of another universe, I think, is by definition unscientific. Because if we can't make an observation of that universe, its existence as part of a scientific theory is not verifiable or falsifiable. So I think any universe, we'll come back to this at the end of the course when we talk about string theory, when we talk about parallel universes, when we talk about 11 dimensions, when we talk about stuff like that. I think any theory that postulates the existence of things outside of our universe is by definition not a scientific theory. Now it should be stressed that this is not a different theory. Okay? It is not saying that anything is different about the observations we make in the universe. It is a different interpretation of what quantum theory means. And all of these interpretations of quantum theory, almost none of them disagree about the fundamental processes and equations of quantum mechanics. In other words, nobody's postulating a different Schrodinger equation. The Schrodinger equation is the Schrodinger equation, and everybody agrees on it because it works. When you solve it for the hydrogen atom, you get all the energy levels of the hydrogen atom exactly, and you get even the weird little intricacies of the hydrogen atom, like the fact that if you put it in a magnetic field, all the energy levels split in two. I mean, we haven't delved really deeply into the hydrogen atom, but the Schrodinger equation explains it to phenomenal accuracy. So nobody's questioning whether quantum mechanics is right or is a good theory. The question is, what does it mean? And what do the entities of quantum mechanics, namely the wave function, correspond to in capital R reality? So far I've talked about sort of three interpretations. One, the statistical ensemble interpretation, which just says that the wave function is just like a histogram for rolling dice. It just tells us probabilities. It's not a real thing at all. Two, the Copenhagen interpretation, which is that the wave function is a real thing. It is the wave function for an electron is as much a part of an electron as the charge of that electron or the mass of that electron. It is a real property that an electron has. When we measure something about it, it changes, and those changes can be non-local, and we just have to live with that. And the many worlds interpretation, which says that when we make an observation, we are selecting a certain actuality from a set of possibilities, but in fact, all those actualities are equally real in some parallel universe where the other observation is made. So it's not that that we are somehow changing the particle, but the particle is manifesting all of its possibilities in parallel with one another. And another interpretation, which is slightly more complicated, and I think probably the most reasonable one, is, I'm not even sure I can explain it, but I'll give you the word for it. It's called decoherence. Or how do I explain the decoherence model? Basically what the decoherence idea says is once a quantum phenomenon gets magnified up to the point where it involves not just one particle or one atom, but thousands or millions or billions of atoms, that the different wave functions for those billions of atoms, the interference pattern between them basically forms one answer that's the right answer, and all the other ones go away. Think about the atom and the Geiger counter. Right here we've got a uranium atom, 92 protons and 100 or so neutrons, and it decays and gives off an electron. Okay. We can talk about the quantum state of that as a single particle. We can write that quantum state down. But when we start talking about a Geiger counter, even the photodetector of a Geiger counter probably has 10 to the, let's be conservative and say 10 to the, if we want to talk about just the photodetector, or just the photomultiplier tube that detects the particle, let's say a billion, so 10 to the 18th atoms. It's probably way more than that, probably another factor of 10,000. But let's just say a billion atoms. What if we wanted to express the state of the Geiger counter quantum mechanically? We would have to write the wave function for all those atoms. In other words, did this atom experience the decay of this electron or not? So I would write the wave function of atom 1 equals half yes plus half no. The wave function of number 2 equals half yes plus half no. The wave function of the millionth atom equals half yes plus half no. The wave function of the 10 to the 12th atom, the trillionth atom, equals a half yes plus a half no. And I would write the wave function for all these atoms. And then the wave function for the whole Geiger counter, which before, just as kind of a shorthand, I wrote as half clicked but half not clicked, is really the sum, really the product of the wave functions of all these atoms that make it up. Million, billion, trillion, etc. Just like in the last class when I showed you what happens when you take the sine with one frequency and the sine with a slightly different frequency and the sine with a slightly different frequency, you wind up with a wave that looks like this. Basically, the idea behind decoherence is if I have the wave function of a million or a billion or a trillion atoms and I multiply all those things together, the most likely case I'm going to get is that one of those probabilities wins, and the other probabilities have a very, very, very small contribution to the total. And so what the decoherence model is saying is by the time a quantum effect gets magnified to a macroscopic effect, the interference pattern between the yeses and the nos cancel each other out and you get one or the other. So macroscopic things don't have a wave function that's half yes, half no. They have one or the other. That yes or no becomes an actuality by being multiplied a million or a billion or a trillion or a billion trillion times together. The problem with the decoherence idea is that there's a gray area. In other words, the question is, where does it happen? Where can we stop pretending things are quantum? Is it with 10 atoms? Is it with 20 atoms? Is it with 100 atoms? The fact that we can do quantum mechanical experiments with big things, for example, I told you that a beam of light, if you pass it through two slits, makes an interference pattern. I told you that a beam of electrons, if you pass it through two slits, makes an interference pattern. But electrons are tiny. We have actually done this experiment. I'm not sure I can draw this. With buckyballs. Who knows what a buckyball is? Yeah, it's a kind of carbon with how many atoms? Anybody know? I think there is a C80 buckyball. The smallest buckyball is C60. And it's the atoms are actually arranged almost exactly like the vertices in a soccer ball. So a C60 atom is 60 carbon atoms in a lattice that is shaped like a soccer ball. We have actually shot a beam of buckyballs at a screen and observed an interference pattern on the other side. Okay? Now, in some sense, a buckyball is still pretty tiny. But it's not just a single particle. You're talking about 60 atoms of carbon, each of which is 12 protons, 12 neutrons, and 12 electrons. So that's 36 times 60, hundreds of particles forming a quantum interference with one another. Okay. So quantum effects don't just disappear immediately once you get to 100 or 200 or 1,000 or 1,000,000 atoms. They sort of gradually fade away as you go from the quantum realm to the macroscopic realm. But there's no line that we can draw where we can say, okay, here things are all probability and quantum mechanics-y, and here things are real, and they have one answer. Right? It would be nice if we could draw that line, but nobody knows where to draw. Clearly, it's safe to say we do not have to consider our cats that are back at home in the apartment as being half dead and half alive. Right? We know that macroscopically that's not how it works. But it's not clear where we can draw that line between systems we have to treat quantum mechanically and systems that we have to treat, or that we are justified in treating in terms of classical mechanics. The most common interpretation of quantum mechanics is really an instrumentalist. Well, it's somewhere between an instrumentalist position and an ignorant position. It's called the shut up and calculate theory of quantum mechanics, which is the approach taken by most real, honest-to-goodness physicists, who say, look, I don't really give a damn about all this philosophy of science stuff, and I really couldn't care less what the wave function means. All I want to know is what equation to plug my stuff into to find out what the energy of this beam of electrons coming out of this tube is in my lab. Okay? The point being that quantum mechanics, in a very important sense, is right. It gives us the right answers all the time. We might quibble about how to interpret the entities of the formulas that give us the right answer, but it never gives us the wrong answer. So if we are, I erased it, instrumentalists, and the problem is most scientists are realists if you back them into a corner and ask them what they think about electrons. They'll say, oh yeah, electrons are real things. But the problem is most scientists haven't thought one iota about any of these questions of interpretation of any scientific theory. In fact, if you ask most scientists, are you an instrumentalist or a realist, their answer would be, what the hell are you talking about? I don't know what those words mean because I didn't take a philosophy of science course because I was too busy taking differential equations and, third semester electromagnetism. So what tends to happen, and what tended to happen a lot, especially in the development of quantum mechanics with these guys like Planck and Bohr and Heisenberg and Schrödinger, is it would get the job done in their 30s, which is when most physicists produce their most productive work. And then when they're 60, 65 years old, they'll write these books, like Heisenberg wrote a book called Physics and Philosophy, where they will wrestle with these questions. Because once you hit 50, all the young people are doing all the important work, and you're too old and slow to get it done anymore. So you write these histories of your field, and you write these philosophical treatises, and you go back and reflect on exactly what it is you've been doing for the past 30 years. Most working scientists don't have the time to worry about things like interpretation. They're too worried about getting their vacuum system in the lab to work and do the day-to-day things that doing science requires. So most physicists don't consider the interpretation of quantum mechanics to be really a very important question. And the people that I hesitate to call it work, the people that wrestle with these questions tend to be philosophers of science and tend to be scientists who are interested in sort of foundational issues, which is a very, very small number of physicists. So, actually, pretty good time. If you read in, as we finish up with the Guillemin book, we're skipping over a big section in the middle of this about particle physics, because it's pretty obsolete. This book was written in 1969. We've discovered an awful lot of particle physics since 1969, which is why I'm having you buy the theory of almost everything. But if we skip past that to, I think it's chapters 16, no.
This is 15 on the series.
I think it's chapters 15, 16, and 17, actually. Guillemin talks about some of these interpretations. Chapter 16 is about causality, what it means for one thing to cause another. Chapter 17 is about free will. And chapter 18 is about determinism, free will, and the new physics. And he kind of I think in a very sort of sober way, lays out some of the relationships between quantum mechanics and some of these wackier interpretations of quantum mechanics. And so those would actually be a really good resource while you're writing your paper for the next 3 weeks or so. Some people try, I think, too hard to make this microscopic, macroscopic connection into something meaningful. I'll give you one example. There's a scientist named, I always blank on it when it comes time to talk about him. The Emperor's New Mind by Roger Penrose. And Roger Penrose makes much of, he's really interested in consciousness. He's really interested in human consciousness and free will and the things that we think we have because we have brains. And if you think about your brain classically, in other words, the way Newton would have thought about a brain is a big blob of chemicals that at some level is just made out of atoms and molecules that are exerting certain chemical forces on one another of attraction and repulsion that will combine in certain ways, and they exchange electrons with one another, and there's all this sort of neurotransmitter business going on in your brain. But it's really all atoms and molecules. And if classical physics were right, and I think we talked about this before, if classical physics were right and we could determine where all those atoms and molecules are and where they're moving and what forces they're exerting on their neighbors, we should be able to do what? Yeah, predict what you'll do, what you'll think, what you will perceive at any point in the future, which is what we call determinism. Determinism is the idea that the universe unfolds, the future unfolds deterministically based on the present. Notice that quantum mechanics kills determinism, right? Because it introduces probability into the mix. And saying, if you've got an atom here and an atom here, there's a certain probability that they'll do this and a certain probability that they'll do that, and we don't know any of their positions exactly. So we don't have to worry about determinism if we believe quantum mechanics. If you like the idea that you have free will, that's good news, right? If you don't like the idea that everything you do in the future is uniquely determined by the current configuration of atoms in your brain, quantum mechanics might be something you like. Go ahead, Mike.
If you believe in that kind of determinism, and if you believe that you could predict, every atom in the brain, like the atoms in the brain are dependent on what's happening around the person.
Yes.
So you have to not only determine all the atoms in the brain, but also all the atoms around the person.
Yes.
And everything that's happening around the person.
Right. So you can never.
You have to do both.
Yes, and you can, so it's never been a practical consideration. Mm-hmm. But we still like to think that what I do tomorrow is not uniquely determined by what's happening today, that I'm able to choose. There's no place for choice here, right? There's no place for the brain to decide where the atoms go. Now, quantum mechanics gets rid of the determinism, but it leaves us with a bunch of probabilities. It leaves us with this atom and this atom have some wave function, and who knows what they're going to do next. There's some probability involved. Penrose likes to... how do I want to phrase this? Penrose is after consciousness. He's after the question of how a bunch of molecules make a being that both seems conscious of its surroundings and itself, and seems to have free will. It seems like I can decide at any given moment whether I want to do A or B. And what Penrose does is he ties this to quantum mechanical effects. If we go all the way down to the level of neurons in the brain, which are these crazy cells that can communicate with their neighbors with electrochemical signals, if we go all the way down to this part of the axon of a neuron where there are actual electrical currents flowing through them. Penrose says that quantum mechanics actually plays a role in the question of whether or not one neuron will signal another neuron. And it's the indeterminacy of quantum mechanics, the fact that quantum mechanics is not definite, that it's based on probabilities, that somehow explains why we have free will, why the brain is not deterministic, why we can decide what to do in any given moment. So he's tying indeterminacy and probability at the quantum level to consciousness and free will at the macroscopic level. Consciousness and free will. And I think Penrose is really barking up the wrong tree as far as a description of consciousness and why we have it. The analogy I often give is trying to understand what the brain does by looking at quantum mechanical effects inside of neurons is like trying to understand why there are traffic jams by studying brake fluid. Right? It is true that traffic jams at some level are caused by brake fluid. Right? If there were no brake fluid, there would be no traffic jams. There would be lots of accidents, but there would be no traffic jams, right? Because when you press on your brake, it is the brake fluid that compresses and causes those brakes to stop and causes all the cars to stop. So on some level, traffic jams are caused by brake fluid. But it's not an interesting kind of cause, right? That is not the thing that makes traffic jams happen. Traffic jams happen because of the reactions of one driver to another driver. And looking at sort of mathematics and physics of traffic is really, really interesting. The fact that you can have one person slam on their brakes on a really, really crowded highway that causes cars to bunch up. And that spot in the road with cars that bunch up will stay bunched up long after that initial car is miles away. In other words, that bunch up is a persistent phenomenon of the cars that the cars go into and they come out of. But the little bunch up stays at that point in space for a very, very long time. So it's not... The cause of that bunch up is the interaction between cars, and it's the sort of psychology of the drivers. It is not the brake fluid, at least not in any sort of interesting way. So if we ask what causes consciousness, yes, the fact that there are electrons flowing through our neurons has something to do with it, but not in any sort of interesting way. The thing that causes consciousness is the interactions between millions, billions, trillions of neurons with one another. Okay, that's where the interesting thing is happening. Nothing interesting is happening here. It's just electrons either going or not going from one place to another, neurochemical